Let's compare the revenue that the auctioneer would get if they used the second price auction to sell the item that they're selling versus the first price auction. We'll stick with the setup that we had earlier where we analyzed the first price auction, where we have two bidders and their valuations are distributed uniformly between 0 and 900. Let's look at the second price auction first. Each bidder bids their valuation in the second price auction, as we saw. So the expected revenue is the expected value of the second highest valuation, because the payment is going to be the second highest bid, which is the second highest valuation when they both bid their valuation. Let's calculate that. The way we're going to do that is to take V1 as given, calculate the expected value of the second highest valuation conditional on V1, and then take the expectation of that with respect to V1. Sounds a little complicated, but we'll walk through it. So given V1, the expected value of the second highest valuation is, if V1 is the second highest valuation, so if V2 is at least as big as V1, then it's just V1. On the other hand, if V2 is smaller than V1, it's simply the expected value of V2 conditional on V2 being smaller than V1. So the expected value is this. We know what this probability is. This is the probability that V2 is less than V1, so that's just V1 over 900. Now this expectation, the expected value of V2, given that V2 is smaller than V1, turns out to be V1 over 2, half of V1. And that's because we're working with a uniform distribution, so it's V1 over 2. Just to make things clear, we've got 0 to 900, and if we had some V1, but we know that V2 is smaller than V1. So if all of these numbers are equally likely, the average of those is just going to be the midpoint, V1 over 2. And that's why the expected value of V2, conditional on V2 being smaller than V1, is V1 over 2. Given that this probability is V1 over 900, this probability is just 1 minus that. So this thing is 1 minus V1 over 900. So we can simplify this expression a little bit. So this whole thing is equal to 1 minus V1 over 900 times V1 plus V1 over 900 times V1 over 2, which is V1 minus V1 squared over 900 plus V1 squared over 1800, which is just V1 minus V1 squared over 1800. Okay, if we know what V1 is, then the expected value of the second highest valuation is going to be V1 minus V1 squared over 1800. Now what we need to do is take the expected value of that. The expected value of the second highest valuation, without conditioning on V1, since we don't know what V1 is the expected value of V1 minus V1 squared divided by 1800. Well, how do we find that? Well, we have to take an integral here. We take the integral from 0 to 900 of V1 minus V1 squared divided by 1800 times the density. So the density is 1 over 900, and we take the integral of that. Don't worry too much about solving this. I'll walk you through it, but I don't expect you to be able to do this on your own. So if we simplify this, we can pull out the 1 over 900. 0 to 900, V1 dV1 minus 1800. V1 squared dV1. So we've got then, so that in turn becomes 1 over 900 times the integral of V1 from 0 to 900 is V1 squared over 2, value it as between 0 and 900, minus 1 over 900 times 1 over 1800, which I'm going to write down as 900 times 2. So this becomes 900 squared times 2. And then we've got here V1 cubed divided by 3, evaluated between 0 and 900. This guy is 900 squared divided by 2 times 1 over 900 minus 1 over 900 squared times 1/2 times 900 cubed divided by 3. So we can cancel this with the cube and cancel this with that. So we get 450 minus, not 900 divided by 2 is 450, divided by 3 is 150, so that's equal to 300. So the expected revenue that the auctioneer will receive from the second price auction is then 300. So let's try the first price auction now. So as we solved in the previous video, each of the bidders is going to bid half their valuation. So the revenue under the first price auction is the highest bid. So it's half the highest valuation. So we'll do a similar exercise. We'll take V1 as given, calculate conditional on V1, the expected value of half of the highest valuation, and then take the expectation of that. So if we have V1, if V2 is bigger than V1, then the expected value of half the highest valuation is V2 over 2, conditional on V2 being bigger than V1. And if V1 is the bigger of the two, then it's just V1 over 2. So let's write this out. Remember, this is probably the probability of this is 1 over 900, is 1 minus V1 over 900. The expected value of V2 over 2, conditional on V2 being bigger than V1, is 900 plus V1 divided by 2 divided by 2. Written more simply, 900 plus V1 divided by 4. Where did I get that from? Let me just give you a quick explanation of that. Remember, we're using a uniform distribution. So if we have 0 to 900, and we have, let's say, V1 here, and V2 can be anything here, and they're all equally likely, then the average is the midpoint. V1 plus 900 over 2 is the average. And so V1 plus 900 over 2 divided by 2 is the expected value of V2 over 2, conditional on V2 being bigger than V1. Plus the probability that V1 is bigger than V2, which is V1 over 900, times V1 over 2. So let's simplify this to 900 plus V1 divided by 4 minus V1 over 4 minus V1 squared divided by 900 times 4 plus V1 squared divided by 900 times 2. Here we can actually split the first term into 900 over 4 and V1 over 4, plus V1 over 4 minus V1 over 4 cancel, and we can subtract this from this, so we get 900 divided by 4 plus V1 squared divided by 900 times 4. That's the expected revenue given V1. Of course, we need to calculate the expected revenue without knowing V1. So the expected revenue is the expectation of this whole thing with respect to V1. So it's expectation of 900 divided by 4 plus V1 squared divided by 900 times 4. 900 divided by 4 is a constant, so we'll just leave that aside. Plus, we'll factor out the other constant here, plus 900 times 4 times the expectation of V1 squared, which is just 900 over 4 plus 1 over 900 times 4 times the integral from 0 to 900 of V1 squared times 1 over 900 dV1. So we've got 900 over 4 plus 1 over 4 times 1 over 900 squared times V1 cubed divided by 3 evaluated between 0 and 900. So that's just 900 divided by 4 plus 1 over 4 times 1 over 900 squared times 900 cubed over 3. So we can cancel the 3 with the 900 to get 300. So we get 1200 divided by 4, which is 300. So what we see here then is that the expected revenue from the first price and the second price auction are both 300. This is not a coincidence. It's not just for this example. This is actually true very generally. So under a very broad set of circumstances, the first and second price auctions are going to give you the same expected revenue. In fact, there are many auctions that would give you the same expected revenue. As long as the bidder with the highest valuation wins in the equilibrium and the losers pay nothing, then you get exactly the same revenue from any Bayes-Nash equilibrium of any auction. This is called revenue equivalence, and it's one of the most important results in auction theory.